This is video number 2 for sections 7.6 and 7.7, examples of solving 3 by 3 systems. I thought it would be good just to practice with another couple of examples. In fact, what you might want to do is try these two examples yourself and then come back to the video and make sure that you showed all the steps correctly. All right, for this first example, it's just another of the same type as we were doing before. I'm looking for an ordered triple of x, y, and z, and those three numbers should make all three of these equations true. Let me go ahead and number my three equations. The first decision I need to make is which letter I'm going to get rid of twice. And I just kind of glanced through looking to see if any of them look particularly nice to deal with. What I notice is that if I focus on the x's this time, in the first two equations, I could add those right now and the x's would drop out. So I think I'm going to get rid of x twice. I will start with equations 1 and 2, and I will add those two equations together so that the x's drop out. Negative x plus x is gone. Y and negative 2y makes negative y. And then I have 4z, and I have 11. I'll call that equation 4. That's the first one where there's no x's. Now I need to find another one where there's no x's. Well, remember, you go back to the beginning. You can either add together equations 2 and 3 or equations 1 and 3. What I notice is, at least in equations 2 and 3, one of them's already a positive and one of them's already a negative. Remember, I'm focusing on x. It wouldn't help you to get rid of another letter now. You have to get rid of the same letter twice. So I'm going to work with equations 2 and 3. Of course, if I were to add these two equations together right now, that would not do me any good. I need the x's to drop out. I'm going to have to do a multiplication trick. It looks to me that if I take the top equation and multiply through by 2, then the x part will become 2x, which is what I need so that the x's will drop out. So let's go ahead and do that down here. That's going to give me 2x minus 4y plus 6z equals 10. I just multiplied every single part by 2, and now I can add these two equations together. The x's drop out. I get negative 3y plus 4z equals 9. Every little sign and all that matters, of course. You got to be real careful with these problems. This is now equation 5. When you're down to equations 4 and 5, you should have two equations that only have the same two letters in them. And that's exactly what I have. I'm down to now just y's and z's. Now I copy those two equations down together, and I simply treat this now as a 2 by 2 system. In a sense, I start all over. Now I got to figure out one of these letters to get rid of. It looks to me like the z's are going to be pretty easy. They almost match now. I'm just going to have to take one of the equations and multiply through by negative 1 to make it work out. That equation would now be positive y minus 4z and negative 11. And now if I add together these two equations, that gives me negative 2y equals negative 2. That's equation 6. That's the one I'm always hoping to get to, the one where there's only one letter, because then I know that I'm basically done. Divide both sides by negative 2 here. My first answer number is y equals 1. And now I just have to trace my way back through these different equations to find the values of the other two letters. Essentially, you find them in the reverse order that you got rid of them. So we got rid of x first. We're going to be finding x last. We got rid of z second. We're going to be finding z next. Then it was the last one to go out prior to the y being found. How am I going to do it? Well, you're going to go back to either equations 4 or 5, whichever one looks easier. Equation 4 looks pretty easy to me. I'm going to copy it down here. In place of the y, I will write a 1. So negative 1 plus 4z equals 11. Carry out the simple algebra, and we'll be done. And I get z equals 3 for that value. We're almost done now. We just need to find x. Well, x exists back in equations 1, 2, and 3. So I need to pick one of these now to plug into. The one that catches my eye is equation 2 because the letter x looks pretty simple in that equation. So I would now take this guy, recopy it, but fill in my values for y and for z. So I have x minus 2 times 1 in place of the y, plus 3 times 3 in place of the z equals 5. Solve this little equation and we'll have x. That's x minus 2 plus 9 equals 5. I believe that's a 7. And then when I subtract 7 from both sides, I'm going to end up with x equals negative 2. As far as giving the final answer to the problem, you state your answers to these problems as ordered pairs. So x comes first, followed by y, followed by z. This would be the solution to this system. All we're saying is that if you go back up to the original three equations and substitute in these three numbers, all three equations will be true. Let's look now at the second example. This one is interesting because this one sometimes throws people off because it looks a little bit funny. You can see the system here. Once again, it's a system of three equations in three variables. It's just that some of the equations don't have all three variables. Actually, none of them have all three. I've written it in such a way to sort of emphasize the whole, the missing variable. Like this one's missing a z, this one's missing an x, this one's missing a y. And sometimes people feel like this is harder. This is in fact an easier problem to work than the other two that we've done. Remember that our starting strategy is you have to get rid of one variable twice. Well, the thing is, some of these equations are already missing one of the variables. So I think we're going to be able to get away with just getting rid of one of the variables once, and then we'll be able to pair that with one of the other equations that already exists. Let's number our equations as usual. And of course, I'm always looking to see where would be an easy variable to get rid of. What catches my eye this time are the z's, because I see that this one has a minus and this one has a plus. So I think I'll take equations 2 and 3. Notice I've written the equations with the wholes still intact. I think that'll be helpful for us in just a second. I am not ready to add these equations together right now because, remember, I'm trying to get rid of the z's, and that wouldn't happen yet. I'm going to have to do one of those multiplication tricks. It looks to me that if I multiply the top equation by 2, that'll set it up quite nicely. Let's go ahead and do that. That'll give me 6y minus 2z equals negative 28. And now I'm ready to go ahead and add these two equations together. I like the wholes because I can only add x's with other x's, so there are no other x's. That's just x. And I can only add y's with other y's. There are no other y's. Remember, these are the two equations that we're adding together. So that just gives me plus 6y. The z's drop out, and the numbers give me negative 23. We've been calling that equation 4. Now, in the last couple of problems, we've gone back to the drawing board then, and we've said, well, which other equations am I going to add together? You don't need to do that this time. I just need some other equation that also has the z missing. Well, I already have that right here. Equation 1 is essentially functioning this time as that equation 5. It's the one that already has a z missing. So I can go right to the next step. I can pair equation 4 and that original equation 1, which we're now calling equation 5, and form my system of equations. Let's do that. Okay, now I need to eliminate another variable. Neither one is really that great. I guess the x's have smaller numbers, so maybe I'll focus on the x's. I'm going to have to do a multiplication trick. Negative 2 would work. so that I can turn that x into a negative 2x. That's going to give me negative 2x minus 12y and positive 46 when I multiply that out. And now I can take those final two equations there, these two equations, and I can add them up. The x's drop out, the y's, negative 11y, and the numbers 44. We've been calling that equation 6. That's the big finish equation because now there's only one letter left. I can easily solve for that letter, and I end up with y equals negative 4. Now that I have that one, I just backtrack my way through these other equations. X was the last one to go out, so it's the next one I'll find. I'll need to use either equations 4 or 5 for that. Equation 4 looks pretty good, so I'm going to take equation 4. I'm going to recopy it, but in place of the letter y, I'm going to put a negative 4. And then I just need to carry out the algebra and I'm all set. Looks like this is x minus 24, and when I add 24 to both sides I get x equals 1. So there's my x value, and then the last thing would be to figure out the z. I'm going to have to go back to one of the equations that has a z in it. That's typically equations 1, 2, or 3, although of course in this case equation 1 doesn't have a z, so I think I'm stuck with either equation 2 or equation 3. How about equation 3? Either one will work. They both have to work because we're looking for numbers that work in all of the equations. Okay, so I've got the x value plus 2z is equal to 5. And again, thankfully, the algebra steps here are simple. It looks like to me I'm about to end up with z equals 2 after I divide both sides by 2. My final answer is the ordered pair 1, negative 4, 2. Anytime you've got some holes in your equations with variables missing, your work is actually a little bit easier. Keep that in mind when you look at the homework problems.